This material will cover inverted lecture 2, and this is going to be involving the strength of acids as they relate to the conjugate base stability. Okay, so remember that acid strength is pKa, and you will have these 2 pages of a pKa table available to you on an exam. But you should be familiar with general ranges and what the different types of functional groups are in relation to pKa. And so let's keep in mind that a stronger acid has a lower pKa, and an acid is a H+ donor. So in the last lecture, we had discussed that if you have an equilibrium reaction, which is an acid-base reaction, you could identify the acid and base on each side of the reaction along with the conjugate partner. You look up the pKa in the table of the acids on each side of the equation, so here and here. And then the direction of the equilibrium is away from the stronger acid. And so we have 4.8 versus negative 1.7. The lower number is the stronger number, so the equilibrium is away from this, which would be this top arrow. Okay, it would be favored to the left, which is the reactants. So when we talk about acid strength, why is hydronium a stronger acid than a carboxylic acid? And so we're going to have 5 factors in this section that talk about acid strength. And it is important to note that the strength of an acid is directly related to the stability of its conjugate base. Okay, so a strong acid equals a weak conjugate base. I had mentioned this before, that it's an opposite relationship when you have a conjugate relationship. If one is strong, the other is weak. When we say weak conjugate base, we mean stable. Okay, so the 5 factors that can result in a stable conjugate base are resonance, and this can stabilize the extra electron density that occurs on the conjugate base, the larger size of the element that's taking on the electron density, the electronegativity of the element, the S character of the hybridized orbital, and then solvation or hydration of the conjugate base. And so the solvent is important, and this relates to the intermolecular forces that we learned in chapter 2. And lastly, a neutral conjugate base is favored over a negatively charged conjugate base. And so just to briefly review, because this was mentioned before, if H3O plus is our acid, our conjugate base is H2O, which is neutral. We lost an H plus. H2O, if you lose an H plus, becomes OH minus, which is negative. And so in this case, the stronger acid had the more stable conjugate base, which was neutral. So neutral is better than negative if you have that option, and that relates back to the pKa. So let's talk about each of these 5 factors, starting with resonance. So remember that resonance is stabilizing because you're spreading out the charge over more than one atom. And this term is known as delocalization. And the arrow pushing we used shows this delocalization, and you have to still be able to push arrows for resonance. Okay, and just a reminder, you're moving electrons only and not atoms, and the real structure is a resonance hybrid. Okay. So let's look at a series where the only difference would be resonance. So here we have 3 acids. In this case, you have to be able to pick out the acidic protons. So we have an alcohol. This is the acidic proton. We have a carboxylic acid here, and this is the acidic proton. And this is a functional group that you did not learn, but I think it's obvious that this is the acidic hydrogen. And you can see the pKa of each of these, with the negative 1.2 being the strongest acid. And so we're going to rationalize how resonance plays a part in that. Okay? Remember, strongest acid equals most stable conjugate base. Okay? So the conjugate base of each of them structures are drawn here. We have the O- for the alcohol, the O minus for the carboxylic acid, and the O minus for the sulfonic acid. The O minus of the alcohol is bearing the negative charge just on this oxygen. However, the negative charge on this oxygen can resonate, and so we can push electrons here and up onto this oxygen, resulting in this resonance structure. This is the hybrid. The hybrid you don't have to be able to draw, but it's important to realize that the negative charge moved effectively from the oxygen through the carbon to the other oxygen, and so it's spread over 3 atoms. So that's better than just being on one atom, and that's why you see the drop in the pKa. For the last case, you can resonate to either side now. And so I'm going to push it onto here, which results in this structure. And then furthermore, this can push down to here onto this oxygen and result in a third structure. So the question is, how many atoms is the negative charge spread over in this structure? So it's spread over each oxygen and the sulfur. So the answer here would be 4. So 4 atoms. Okay. So what's important and the takeaway from this is that the more resonance structures you can have of the conjugate base, the more stable that conjugate base is. Remember that stability was weaker conjugate base. And then how does this relate to the acid? A weak conjugate base equals a stronger acid. And so our answer here was most resonance, strongest acid. And that's what this is taking you through that reasoning. So reason 1 was resonance. Reason 2 deals with the size. And so when you're comparing size, you want to compare a similar series. And so we have the hydrogen halide acids shown here, from fluorine to iodine. And you want to focus on the atom where the negative charge is going to end up. Don't look at the whole rest of the molecule. So who accepts the charge in the conjugate base? And then keep in mind, as you go down the group in the periodic table, the size increases. Okay, so fluorine, chlorine, bromine, iodine is going down a group. If we write the conjugate base of all these, we see these 4 here. Of these, the HI is the strongest acid because it's the most negative number. And now we learn, since iodine is the largest, it is the most stable conjugate base, okay, right here, which is the most acidic. Okay, so it relates to a size argument. Here's another example down here. We have an oxygen acid versus the sulfur acid, and I circled the acidic hydrogen. To draw the conjugate base, remember that you lose H plus each time. And so the electrons go back onto the oxygen or sulfur, and here are the conjugate bases. The sulfur version is more acidic, and you ask yourself why. If you refer to the periodic table, sulfur is below oxygen. Sulfur is larger than oxygen, and again, the larger size has the more stable conjugate base, which is the stronger acid. The third reason is electronegativity, which we're already familiar with. Remember that electronegativity increases up and to the right. And so if we have carbon, nitrogen, and oxygen, oxygen prefers to have the negative charge over nitrogen or carbon. And that example can be seen in pKa's. When you have oxygen attached to a hydrogen, that hydrogen is more acidic than if you have hydrogen attached to nitrogen. That's less acidic. And then H attached to carbon is even less acidic. And so the acidity series here relates to electronegativity. The second thing that deals with electronegativity is hybridization. And so we had used this term S character before. An sp orbital has 50% S character because it's half S and half P. An sp2 orbital has 1/3 of S, and so that's about 33%. And sp3 has 1/4 S, which is 25%. So this has the least amount of S character. and we want more S character is more acidic. Okay, so more S character equals more acidic. And so here's a range of the hybridization shown here, and you can see that this is the most acidic because it's the lowest number, and this carbon is sp, or in this case your carbon is sp2, and here it's sp3, and that's the relation to acidity. And this is not just for carbon, it can be for any atom. Okay, I'm just showing you a series of carbon, but you should be able to do the same reasoning for a series with oxygens or nitrogens, for example, where they're just changing the hybridization. Okay. The last aspect of electronegativity to discuss is how close you are to an electronegative atom. The third point dealing with electronegativity is that an electronegative group near an atom accepting the negative charge can still have an effect, and this is known as the inductive effect, which is a through bond effect. And here's an example of that, number 3. The fluorine is attached to this carbon, which creates a dipole, putting a partial positive on this carbon. However, the carbon next to it also experiences a partial positive, but I have it smaller just to show you that it's not as strong of an effect. And so this is the through bond effect. Even though the fluorine's not directly attached to this carbon, this still feels the effect of the fluorine over here. And so I've listed that carbon 1 is more electropositive because of the partial positive than C2 because it's closer to fluorine. So this one's more positive than this, but this still feels that effect. And an example of that in action is here with this alcohol. So here are 2 different alcohols and the acidities associated with them. Okay, the top one is more acidic because it has a lower pKa, and it's because the fluorine here is pulling electron density through this carbon, through the oxygen, and then to the H. So it can feel that effect, and it's more acidic than a very similar structure, where instead of fluorine you have H. Okay? So watch out for fluorine or other electronegative groups somewhat near the actual somewhat near the atom that's connected to where the acidic hydrogen is. But it's not directly connected. So you see here that it's still oxygen in both cases, but the fluorine is further down the chain. The last point, which is, I don't want to focus too much on this, but just to say the solvent is important. And so the conjugate base exists in a solution. And so let's say here we have a conjugate base of an alcohol, this O-, and it would be polar. Okay? And it can be in 3 different solvents: hexanes, diethyl ether, or water. And so in terms of solvents, the hexanes are nonpolar because they're just CH. So we have a polar and nonpolar, which is not a great match. Diethyl ether, on the other hand, is polar. Remember, ethers are polar because they have a net dipole. Okay, so we have a polar-polar match, and this is a good situation. In this case, water is also polar, and it can hydrogen bond. And so again, we have a polar-polar match, which is good. Okay. The one thing I want to point out in this last situation is that the H here is somewhat acidic, and so you have to be careful when using water, for instance. And so I have here, be careful for OH and NH on solvents. These are called polar protic solvents, and the protic means they have an acidic hydrogen. Okay. And the problem with these is that they can actually undergo an acid-base reaction with your conjugate base. And so in this case, if we have water and we have CH3Li, remember that this is the same as CH3 minus Li plus in this case, this negative charge is reactive and can just pull off the hydrogen here. And so we actually have a reaction, and this is not a good combination. Before we go to the practice problem, I just want to mention a concept I forgot on a previous slide to mention. So if we go back to slide 16, we were talking about a size argument. And one thing that can be a little bit confusing is these two molecules here. We have an alcohol and we have an alcohol. And this has a larger group on it, right? 3 CH3 groups. If you draw out this molecule, it looks like this. This is a bigger size molecule than that. But this is not an example of a size argument, because remember, the size argument, we need to focus on the atom where the negative charge is going to reside or where the electrons will end up. As you can see here, the I minus, we can make a size argument because the negative charge is directly on the iodine. But in this case, these are our acidic hydrogens. And so the negative charge is going to end up on the oxygen. The oxygen is the same size. Okay, so don't be misled by big groups near. That does not change it. So only if the group itself is larger, like in this case, oxygen and sulfur. And so if you're going to make a size argument, you have to focus on elements in the same group. Okay, so you want to look for elements in the same group on the periodic table. All right. Okay, so let's go to the last practice problem. And this is kind of putting the concepts together again. And we're going to look at this equilibrium reaction. The products are drawn for us. And so we're going to predict the direction of the equilibrium reaction. We're going to also point out the conjugate acid-base pairs. And we're going to now argue why this equilibrium exists. Why is one a stronger acid than the other? Okay. So for acid-base reactions, we want an acid and a conjugate base on each side. Okay, so let's draw in all the lone pair electrons. This is an amine functional group, so it's going to have a lone pair here. And this is a hydronium. We'll have a lone pair. The lone pair here is gone because now the nitrogen has 1, 2, 3, 4 bonds, and so there's no lone pair. And the oxygen now has 2 bonds to hydrogen, and so we'll have 2 lone pairs. Okay. So what is acting as the acid? Who is losing the proton? It's the hydronium. It has 3 here and only 2 here. So this is serving as our acid. This must be our base. And then we have the conjugate acid and conjugate base. So if this is the acid, it has a conjugate base. And if this is the base, it has a conjugate acid. So we look up the pKa for acids only. So we want the pKa of hydronium. And so you should have your pKa table with you. And so for instance, here is the pKa of hydronium. H3O plus is negative 1.7. So we will write that on here. And then the pKa of this acid, which is an ammonium because it has a positive charge. Okay. And you see that we have some examples of ammoniums here. And so we want to pick the closest one. This just has a methyl group. And just looking through, we have an aromatic group attached here. And so I don't see any that are just a phenyl group. Methyl group, I mean. So let me come on to this chart, and I'm scrolling down still. And here we have it right here, CH3, NH3 plus. So this is 10.7. Okay. So the equilibrium is always away from the stronger acid, and so this is the stronger acid because it's the lower pKa. And therefore the equilibrium is going to reside to the right. Okay. So predict the direction of the equilibrium, the conjugate acid-base pairs. Moreover, we can push electrons just for added benefit. The nitrogen picks up the extra hydrogen here, and so it attacks a hydrogen. And then that has to break the bond and give the water the extra lone pairs. Okay. And now we want to say, why does this exist? Why is H3O plus a stronger acid than CH3 and H3 plus. Okay. So looking at the reasons, both are positively charged and both are going to end up as neutral when they go to the conjugate base. Okay. So we can't make the argument of one going to be neutral. And then we ask ourselves, okay, what differences are between O and N? Okay. In terms of the periodic table, oxygen is to the right of nitrogen. And so when we're arguing across a row, such as this, we're going to argue electronegativity. So oxygen is more electronegative than nitrogen. Okay. More electronegative oxygen, and therefore it can better handle the extra electrons. Because remember, this had one set of electrons and now it has two. This has none and now it gained an extra lone pair. Okay, so because oxygen is more electronegative, it can better handle the extra electrons and therefore it's more stable. Conjugate base. And therefore stronger acid. So after reviewing these lecture notes, you should be able to go through the 5 principles we talked about from the first slide and make arguments based on each of these as to why something is a stronger acid than another and how that relates to the conjugate base stability with these 5 arguments.